All right, everybody, in this lesson, we're going to talk about the self-ionization of water. And to do that, we need to back up a step or two. Earlier in the year, we talked about distilled water and how it doesn't conduct electricity because it's a polar molecule. At the time, I kind of fibbed to you a little bit. And I told you that there was no ions in solution, no ions in solutions, no electrolyte. No electrolyte means no conduction, which was kind of true. But the reality is water actually self-ionizes. So what happens is it actually forms its own little equilibrium with itself, where liquid water molecules form hydrogen ions and hydroxide ions in solution. Now, this equilibrium is heavily reactant favored. So almost all of it is liquid water, but there are some ions in solution here. Take a look at these numbers here. It's 1 times 10 to the negative 7th for each of these concentrations, which would make sense because it's a 1-to-1 ratio. So these would be the same. So you notice these are tiny little concentrations. You know, we're talking about 6 zeros in front of that one there. So it's very, 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 very small amount of it. But it is an equilibrium, which means we can mess with that equilibrium. And that's what acid-base chemistry does, okay? Because neutral solutions of pure water, these concentrations are equal. But as soon as we start adding acids and bases into water to make solutions, we now mess with this equilibrium. Here's a short video clip kind of showing how this happens.
Self-ionization is the process in which two like molecules react to give ions. Water undergoes a self-ionization to form hydronium ions and hydroxide ions. The reaction maintains a steady concentration of each of these ions at 1 times 10 to the minus 7th molar under neutral conditions. The product of these concentrations is the ion product constant for water, Kw, and is equal to 1 times 10 to the minus 14th at 25 degrees Celsius.
If you notice in this solution here, we have water, 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 water. But there's a few places right here where we have an oxygen, which is red, and just a single hydrogen, which is our hydroxide ion. Here we have, looks like 3 hydrogens around a water. And what it is, it's a water molecule, and one of these hydrogen ions has attached itself to that to kind of hang out with it when it's in solution. Okay, we call that a hydronium ion, not important, but that's kind of what it is, all right? And then we see another one down here and another one here. But for the majority of our solution, it is just water, okay? Now, because this is an equilibrium, okay, the hydrogen ions and the hydroxide ions are interdependent on each other. What I mean by that is you can't change one without changing the other, okay? Go back again to Le Chatelier's principle. And, you know, one of the reasons why we spent so much time on that in the previous unit was because in this unit here in acid-base chemistry, we have to be able to recall that principle and use it, okay? You can't have one go up without the other one going down, okay? So they're interdependent. Now, this equilibrium, again, is heavily reactant favored, and we see that with the Kw value. We call it Kw because it's a KEQ, or equilibrium constant, but it's very specific to just water. So we actually give it a special designation as Kw. And it's always 1 times 10 to the negative 14. Okay? Again, look at this number. It's tiny. Okay? Meaning, remember, K values that are smaller or less than 1 are reactant favored. This is heavily reactant favored, almost all water. But we do have a little bit of ions in solution that are hydrogen ions. We have a little bit of ions in solution that are hydroxide ions. When you are neutral, they're both 1 times 10 to the negative 7. Okay? But again, if we add an acid base, we can mess with that. So that's what we're going to do, okay? Now, one last piece of this is realizing this equilibrium expression. Water is not part of it because water is a liquid, okay? If we go back again to our rules, liquids do not have a bearing on equilibriums. So the only thing that really matters in terms of adjusting this equilibrium is the hydrogen ions or those hydroxide ions in solution. So let's talk first about how an acid shifts this equilibrium, okay? So again, we have our equation here. I do need to apologize. This should be a double-headed arrow. I did not do that correctly. So if you put in your notes, go ahead and make that a double-headed arrow because it does go both directions. It is an equilibrium. Here's our expression again. Remembering that this number has to stay 1 times 10 to the negative 14th at all times. So what we're going to do is we're going to add an acid in. Now I grayed out the parts that really aren't important to us, but let's talk through them anyway. So hydrochloric acid gets put into water. It's going to dissolve. It's going to split into hydrogen ions and chlorine ions. Chlorine ions are going to be spectators, but the hydrogen ions are going to attack this hydrogen ion and it's going to cause that to spike. Okay? which means if we see a spike here, the equilibrium will shift to the left over here, which means hydroxide ions will decrease. We'll make more water and we'll stabilize those hydrogen ions by reusing some of them up. But because we actually put extra H plus in solution, the net result here is that we're going to have more H plus overall and the OH minus must go down. It has to happen proportionally because Kw has to stay 1 times 10 to the negative 14. Okay? The net result of this is we can say that the hydrogen ions will always be greater than 1 times 10 to the negative 7th, and your hydroxide ions will always be less than 1 times 10 to the negative 7th. Okay? Or another way of looking at it is when you form an acid, or when you put an acid into water, it's going to create a scenario where your hydrogen ions are greater than your hydroxide ions. Okay? And if you're wondering that we see lots of 7s and 14s and that kind of stuff up here, if maybe your brain is going towards pH scale a little bit in terms of, wait a minute, isn't the pH scale 7's neutral, 14 is the highest? Yeah, and we'll get to why that is here in a minute. And it does have to do with these numbers. Now, bases are a little bit more complex, okay? Because bases can attack it one of two ways. If we use a more classic base from our older definition that has hydroxide in it, okay, that's the easy one to kind of see what happens because it's the exact opposite of what we just talked about. So you're putting hydroxide in, this number is going to go up, it's going to use your hydrogen ions to shift it to the left, and again, as it shifts to the left, we're going to have a net result of more hydroxide and less hydrogen ions, okay? So again, with our first example here, we're going to see that for bases, your hydrogen ions will always be less than your hydroxide ions, okay? However, remember, according to our working definition, bases are proton acceptors, all right? So they either have hydroxide ions in them or they can do this too. So this ammonia could accept a hydrogen ion and it could form ammonium ions in solution. If that's the case, instead of putting more OH in, what we're doing is we're actually removing hydrogen ions. So again, we apply Le Chatelier's principle like we've been doing this whole time. If we remove H+, now the system is going to shift to the right to replenish it, but also make more OH-. The net result is the same. We still end up with an OH- concentration greater than the H+ concentration, okay? So no matter how we stress it, both ways of stressing it, it ends up being that H+ minus, or H+ is less than 1 times 10 to the negative 7th, and OH- is greater than that, okay? Or always for bases, the shift is to less hydrogen ions and more hydroxide ions, okay? So kind of give you an idea of how these things shift these equilibriums.